Hello there. Today we'll be doing a pretty interesting problem called find the duplicate numbers. This is going to be a pretty difficult problem if you've never seen it before. Of course, there is an easy way of solving this, which is going to take us n squared time checking each number against each other number. So what I mean by that is if we take the 1 and we check all the other numbers to see if there's a 1, and then take the 3 and check all the other numbers, that's 3, 4, and then 2, and then we find another 2 and we can return the answer, and that is n squared time, and that we can retain not modifying nums, and we don't use extra space. Of course, if we had extra space, that would be very easy because you can use a hash, or we can modify nums, we could use a sort, and then we could get, go about doing a binary search, or we could even just, n I and then I plus 1. What I mean by that is we're going to take the I and then I plus 1 and check if the one is close to another one is the same, and we're good to go. But we can't do any of that. What we're going to do to bring it down to O of n time and O of 1 space is going to be using a linked list. And you might ask, how do we use a linked list? Okay, so in this particular problem, we are given numbers from n, from 1 through n, and we have n plus 1 integers. So that must mean there's a duplicate, and that also means that we can point to each item using an array. So, and when we point to each item in the array, we can find the cycle in these items. So if you've never seen this before, I don't think that will ever come to you intuitively. The usage of, let's say, this thing called turning an array into a linked list. So let's turn it into a linked list now. So 0 is going to point to 2. 2 is going to point to 7. 7 is going to point to 1. 1 is going to point to 4. 4 is going to point to 3. 3 is going to point to 6. 6 is going to point to 5. 5 is going to point back to 7. And then we have a cycle. You might think this is quite excessive for an example, and you might be right. But I think it gets the point across that we can do this. So with that, we can use a slow and fast pointer, find a location where they meet. So slow, fast pointer, slow pointer, fast pointer, slow pointer, fast pointer, slow pointer, and then we move back to 7, and slow pointer, fast pointer, and one behind, that means the next one will be where they meet. They meet at 6, but the duplicate is not 6. The duplicate is 7, and so the 7 is where the entirety of this begins. So basically, how do we find that? Is that we create 2 slow pointers. So this is going to be slow 2, and we're going to move this forward one at a time. So slow moves forward, slow 2 moves forward, slow moves forward, and slow 2 moves forward, and the position where they meet is the duplicate. Now, how is this possible? Well, this is Floyd's algorithm. What happens here is that the proof is, suppose this is x, this top part. This is the distance before the cycle begins. This is where the this is the distance where we will be doing a lot of cycling, and this is the point where they meet, and after that is going to be L minus y. And you might not wonder where are these variables coming from. Well, here's where the variables are coming from. So let's say the slow, of course, slow is going to be equal to x, yes, and we're gonna travel n times the L, this y, this part, and we're gonna do a plus y, which is this part here. So of course, this is way in advance. Okay, so so NL, and this is Y. So with that, we have fast, which moves twice as fast as this. But this is equal to x plus more times, I don't know how many times, L plus y. But which is also equal to 2s, which means it's equal to 2 times x plus n, L plus y, which is going to give us a way to get, you know, 2x plus 2nl plus 2y equal to 2x plus n 2l plus y. And we subtract everything. Let's subtract the x's from both sides. And we lose the x. Then we subtract 2nl from both sides. We lose the nl. So n 2l minus 2nl minus y. So, and we can separate the l's, of course, to n2 minus 2n minus y. And that also means x is equal to the k of L. So and you're asking me how I found this out. I just did some research. So minus y. With that, this is the k cycles, and this is the y distance. And so that means that x is equal to the distance at which we just need to take y distance forward, and we would meet at the same place. Yeah, pretty interesting stuff. So if you want to do more mathematics, you feel free to check those videos. But we're going to do the algorithm now and show it's how it's done. So slow equals fast equals 0. And so while true, we're going to slow is equal to nums at slow, and fast is equal to nums at fast. So we move twice. So if slow equals fast, we can break, and we have identified the cycle, and we can start slow 2. Equals 0, where we can begin this second cycle. So slow equals nums at slow, and fast equals nums, slow 2 is equal to nums at slow 2 forward. And if slow equals slow 2, then we can return slow. Perfect. With that, we can return the code and get our answer. Oh, that's not the right equal sign. It's a double equal sign. All right. Perfect, and let's submit. All right, so not bad. We have solved the problem. It's a little slow this time around, but I think it can go faster. Right, great, perfect. So that's how we solve this type of problem. Wow, that was interesting, wasn't it? If you enjoyed this video, like and subscribe. Want more videos? Check the link in the description below. And if you have any questions, please comment below. Remember, yeah, check me out. Check out the more videos in the link in the description below. Anything else? I really want to talk about this part because I don't think that was super clear. But I don't think it's ever going to be clear unless you go through this a couple of times. So never mind. Okay, bye.